So in this video, I'm going to go ahead and walk you through how you can determine if a point is a solution to a system of equations. So a system of equations just refers to if we were to graph two lines on the same coordinate plane, where those two lines intersect, this is considered the solution. That solution is a point that's made up of an x-coordinate and a y-coordinate. So when we are given the problem in number 1 where it says, hey, is this point, -4 and -1, a solution to the system of equations, show your work below, what we're going to do is we're going to take this x-coordinate and this y-coordinate, and we're going to go ahead and plug it in to each equation. So where it says y equals x plus 3, instead of writing y, you're going to go ahead and write -1. And where you see x, you're going to go ahead and write -4. And we're going to simplify on both sides of the equal sign. So -1 is at equal to, what is -4 plus 3? That's going to be -1 as well. So -1 is equal to -1, so we know that this point lies on this line. We now have to check that the same thing is true for our second equation. So go ahead and start out by writing your equation out. Where you see a y, you're going to go ahead and replace that with a -1. Where you see the x, you're going to go ahead and replace that with -4. Now, in this problem, it's a little bit different because we have a product of these two terms before we add the 11. So just like we did before, we're going to simplify on both sides. 3 times -4 is -12 plus 11. -12 plus 11 is -1, which is also true. So because this point works for both of our equations, we would consider this, yes, that is a solution. We're not given the graph, but if we were to use Desmos to graph both of these equations, we would realize that they both intersect at this point. I guess it's in the wrong quadrant. It would technically be in this quadrant. Looks something like this, right? Where we would go ahead and they would intersect at -4 and -1. So we don't need to be given the graph. We can just do this algebraically. So let's go ahead and look at number 2. We're given another coordinate point. This is my x-coordinate is 3, my y-coordinate is 7. And you're given two equations just like we were before. You'll notice that these equations, both x and y, are on the same side, whereas in number 1, we had a y variable on one side of the equal sign and an x variable on the other side of the equal sign. So it doesn't matter where your x and your y's lie, you're going to go ahead and repeat the same process. Where you see an x, so this is x plus y is equal to 10. Where you see an x, you're going to go ahead and replace it with 3. Where you see a y, you're going to go ahead and replace that with 7. So 3 plus 7 is 10. And is 10 equal to 10? Yes, it is. So we know that it works for this solution. We now have to go ahead and plug in 3 and 7 to our second equation. So 9x plus 6y is equal to 6. 9 times, I'm going to go ahead and plug in 3 where I see my x. 6, I'm going to go ahead and plug in 7 where I see my y. 9 times 3 is 27 plus 42. Is that equal to 6? No, it is not. 27 plus 42 is going to be 69, which is not equal to 6. So because it does not work for the second equation, 3 and 7 is not a solution to our systems of equations. So not only do I need to be able to plug in a point to verify if it's a solution, but we should also be able to recognize that from a graph as well. So kind of like the little graphs that I was graphing up there before, where these two lines intersect, that is your solution. So if we're asked to give an example, there's only one example here. We're going to go ahead and identify the x-coordinate, +2, and the y-coordinate, 7. So I'm going to go ahead and label that 2 and 7. Now the second part of this is to label this on the graph, which I did, labeled it as a solution. Part B asks, hey, what is not a solution? Well, there are so many options that you can choose from. I can choose this point, I can choose this point, I can choose this point. All of these points are non-solutions because they're not the place where the two lines intersect. So it doesn't really matter which one you choose, as long as it's not this one. And you're going to go ahead and write the x, y coordinate on here. So I'm going to choose this one, not a solution. Again, the x coordinate's -2, the y coordinate's +1. And this is not a solution, and I've labeled it on my graph. In number 4, we have 3 siblings that are participating in a family-friendly running event. The oldest sibling begins at the start line of the race and runs 7 miles per hour the entire time. The middle sibling begins at the start line and walks 3.5 miles per hour throughout the race. The youngest sibling joins the race 4 miles from the start line and runs 5 miles per hour the rest of the way. In part A, we're going to go ahead and match each graph to there's a typo here, they should say sibling, whose running is represented by the graph. So we have to pick up some key words here. For example, the youngest sibling joining the race 4 miles from the start. If we look at the 3 graphs, you're going to notice that graph A is the one that has the starting point or the y-intercept that starts at 4. So we know that graph A is going to be the youngest sibling. I can go ahead and draw an arrow to that graph. Now we're going to go ahead and look at the other details for the oldest and the sibling and the middle sibling. So the oldest sibling runs 7 miles per hour the entire time, where the middle sibling walks at 3.5 miles per hour. So the older sibling is moving faster. So the way that we would communicate faster in a graph would be that we have a steeper slope. I'm able to cover more miles in an hour than I would if I were to walk. So we know that B has to go ahead and match up with the oldest sibling, and then our middle child would be graph C. So once we identify those parts, in part B, we're asked, hey, will the graph A and B intersect? If yes, let's predict their intersection. So let's look at graph A and B. You can see that if we were to continue this in this direction, these aren't very straight lines, that yeah, they would in fact intersect. And we can kind of guesstimate. So we know that it's going to be at the left of 1 hour, but it's not going to be quite 2 hours. So my guess would probably be it's around 1.5 hours of running. And I'm going to go ahead and guess, like if you look here on the y-axis, 2, 4, 6, 8, if I continued that spacing, I don't know, 10, this would be like 12 up here, 12 up here. So you might say, if this is going to be 10 and this is 12, it kind of looks like it's in the middle. So I'm going to go ahead and guess 11. So that means that after 1.5 hours of running, we are 11 miles from the start line. So I say yes. My answer is 1.5, 11. And I'm going to go ahead and interpret that as a sentence. At 1.5 hours, we are 11, is it miles? Let's see. Yep, miles from the start line. Okay, part C, will graph A and C intersect? If yes, predict their intersection. If not, explain how you know. So graph B and C won't intersect again. You could have said that they intersected here at the starting line because they both start at the same place, but because the older sibling is running faster and the middle sibling is walking, they're never gonna intersect unless, for example, the older sibling stops and the middle child or the middle sibling is able to somehow walk or run to meet up with them. But that doesn't look like the general trend. So we can talk about all these what ifs, but just given the information that we have, we can conclude that no, they don't intersect. If you wanted to write something like graph A and C both start at the origin, but will not intersect given the information. So again, information can change, but given the current information, the older sibling running, the middle sibling walking, it's not going to change. They're not going to intersect. All right.